Welcome to a lesson with Dr. Powell. Let's look at an example of how we can prove or show that a set is a subspace of a vector space. We're going to look at our vector space as being R2, and this right here is our set, and we want to show that this is a subspace of this vector space. This set right here is actually the collection of what you would call linear combinations of two vectors, meaning multiples of this vector added with multiples of that vector. Sometimes the notation for the set H could simply be put as the span of 1, 3, 2. This is spanning notation, and it simply means that we're looking at all linear combinations of these guys here. Now, the span of a set of vectors is a subspace. So essentially what we're going to do is we're going to verify that using the criteria that we have for something to be a subspace. So when is a subset of a vector space a subspace? Well, if it's closed under addition, if you take any two vectors in here, like v and u, and you add them together, are you still in H? So v plus u. So if v is in H and u is in H, is their sum again in H? The other thing that we need is scalar multiplication. Let's suppose we take, these are real vector spaces, and let's suppose that you take a real number, scalar, and if you scale a vector v, which is in H, is it still in H? Okay, so is the sum in H, and is rescaling in H, or scaling in H? And those two things are enough to show that that this would be a subspace. What does it mean to be a subspace? Something is a subspace if it's a vector space in its own right, and it's a subset, meaning that it's an additive group with respect to addition, and addition is well defined on it, it's closed on it, and well, it needs to be a group, so it has to have an additive identity and has to have inverses. Do we really get that from all of this? And we do, because -1, happily, is in the real numbers. So if we rescale a vector by -1, you actually get its additive identity. So that's pretty nice. Also, if you have a vector and its additive identity, you add them together, you're going to get the zero vector, or the zero additive identity of R2. So those things we get for free here. If we just simply check these two things, we're going to check that addition is closed in H, meaning just take any two elements of H, add them together, are you still in H? And also, if you take an arbitrary element of H and you scale it, are you still in H? All right. So how do we do this? How do we write a proof for this? We need to take an arbitrary element of two arbitrary elements of H. Look at the set builder notation. The set builder notation for H actually tells you what arbitrary elements will look like. They have this form where A and B are real numbers. So we have V and U. Let's represent both of them with this form. So let's take V and represent it with this form. Suppose that V is simply some number A times 1, 3, 2, plus some number B times 0, 2, 3. Now, what about U? Let's represent it also with this form, but maybe with different numbers, like C and D could be used perhaps to represent the real numbers, but being of that form. So let's suppose this is V, and then let's put U. Let's do C 1, 3, 2 plus D 0, 2, 3. And that could be U. Okay, now adding them together with the addition in the vector space, R2, then what we have, we can rearrange this. We could add this guy with this guy, and one nice property with that has to do with scalars and vectors is we can actually factor out the vector here out of the scalar addition. So a plus c times 1, 3, 2. And we can add to that b plus d times 0, 2, 3. Now notice the sum is now written this way, and realize that this is a real number and that's a real number, and it's in the same form as what we have for elements that are in H. So it is in H, because H is all linear combinations, meaning all things like this times a real number plus all things like this times a real number, and indeed the sum happens to be of that form, so therefore it's in H. So we have just shown that this span right here is closed under addition. Now, is this span closed under scalar multiplication? So let's take a scalar and apply it to a vector v that's in H. Now, it needs to be an arbitrary vector that's in H, or needs to have a description of what it means to be in H, which is something like this. So let's just take that guy, for instance. So times a 1, 3, 2 plus b 0, 2, 3, and this k will distribute through. And when it distributes through, we end up getting k times a times 1, 3, 2 plus k times b times 0, 2, 3. Notice that this is a real number and that's a real number, and it matches the criterion for what it means to be an H, which means, therefore, that when we apply a scalar to any vector in H, we're again in H. So therefore, it is closed in H. We have just shown that this span is a subspace. An equivalent definition for what it means to be a span of two vectors is it is the smallest vector space or smallest subspace that contains those two vectors. That's an equivalent definition to simply stating that it's all linear combinations of these two vectors. Quite minimally, actually, a subspace has to contain linear combinations. And so therefore, since the linear combinations themselves create a subspace, then what we get is it is the minimal subspace. So both definitions are equivalent here, but for our sake and purposes, what we were doing is we were just simply looking at this set defined this way as linear combinations, and then showing that that these two different criteria hold, which put this set H as a subspace of R2. Thanks for watching.